In this lecture, I introduce Orbit, an nDNA-empowered framework for diagnosing the epistemic health of large language models for multi-turn dialogue. Instead of scoring surface fluency or isolated facts, Orbit tracks the latent evolution of beliefs by treating internal representations as semantic trajectories in high-dimensional space. Why this matters now? We are at a moment where dialogue systems sound impressive, yet we still don't know how their beliefs change as a conversation unfolds. Fluency has outpaced understanding. Safety has outpaced diagnosis. If we want trustworthy assistants, tutors, and agents, we must move beyond judging what they say and start measuring how they think across turns. Orbit is that shift, a clean, practical way to read a model's epistemic pulse during dialogue. It watches the inner trajectory of beliefs, not just the surface text, and turns that hidden journey into a simple score and a rich signature. In one framework, Orbit acts as a report card for memory and reasoning, an early warning system for drift and derailment, and a design compass for training curricula and guardrails. With Orbit, we can see when a model is coasting on repetition, score whether it is progressing purposefully or veering off course, and ultimately steer models toward conversations that remember, adapt, and reason with intent. Think of it as moving evaluation from grammar to governance of thinking, from surface plausibility to epistemic interpretability. First question can come to someone's mind is, why aren't surface metrics enough? As scores like Blue, Rouge, Meteor, or Perplexity reward local fluency but miss global coherence. They can't see contradictions that emerge over multiple turns, topic drift, or claims that quietly detach from earlier context. Even learned judges mostly grade outputs, not the internal state changes that produce those outputs. Output-only scores are non-identifying. Identical sentences can arise from careful reasoning or shallow mimicry, so they cannot tell genuine deliberation from pattern replay. Worse, these metrics invite good-hearting. Models learn to imitate judge style and win the rubric without stable beliefs. They are also blind to cross-turn contradictions and to whether later turns repair earlier errors. Most critically, they cannot measure epistemic work, the internal retrieval, integration, and updating that should happen between turns, and they often mistake low-entropy repetition for coherence. In safety-relevant settings, this blindness hides trajectory risks that only the latent path reveals. To evaluate dialogue honestly, we must score the evolution of beliefs, not just the final prose. Multi-turn long conversation leads to the semantic drift problem. Modern LLMs rely on implicit memory, so facts and constraints decay over long conversations. We observe stance reversals, forgotten requirements, and meandering topics. Single prompt benchmarks can't capture this, and for high-risk domains we need guarantees about the entire trajectory, not a one-shot score. What lens can expose this? The answer is latent geometry. As a conversation progresses, latent activations trace a path through representation space. Curvature marks turning points, torsion captures twists in belief direction, and path length measures epistemic work done to reach an answer. By tracking these signals, we don't just detect that drift happened, we start to explain why it happened and how to steer models towards stable, memory-aware dialogue. Orbit measures 4 rewarded signals. First, spectral memory retention. It tests whether the model truly recalls and reuses earlier context by projecting the current belief state into a compact memory subspace distilled from prior turns and rewarding strong alignment with that learned memory. Second, thermodynamic length. It estimates the amount of purposeful internal work within a turn by accumulating the small, layer-by-layer changes in hidden representations, so longer yet smooth paths reflect meaningful reasoning rather than idle echoing. Third, epistemic drift. It captures the net movement of beliefs across the entire conversation by comparing where the dialogue began to where it ends, rewarding appropriate progression that advances goals or integrates new evidence while avoiding stagnation. Fourth, epistemic torsion. It measures how the direction of thinking redirects across successive turns, using triplets of belief snapshots to detect coherent pivots toward new subtopics or constraints instead of aimless zigzags. To keep the score honest, Orbit also applies a semantic coherence penalty whenever cross-turn states collapse into low-entropy sameness, so models are not rewarded for repeating themselves. Together, these forces favor dialogues that remember, transform, adapt, and pivot with intent, anchored in past context yet evolving with the conversation. What Orbit score means in practice? High orbit indicates that the assistant anchors to prior commitments, does visible epistemic work inside each turn, adapts its stance as new facts arrive, and executes clean, purposeful pivots without losing the thread. Low orbit exposes shallow memory, minimal internal movement, random or excessive shifts, and deceptive coherence that is really repetition. In head-to-head comparisons, you will see strong models tracing smooth, low torsion trajectories with compact belief loops, while weaker ones wander through jagged paths that flip direction unpredictably. How to use it? Orbit doubles as a report card and an early warning system. The overall score ranks models for multi-turn reliability, and the component traces show why a dialogue succeeded or failed. A dip in memory retention flags forgotten constraints, an anemic path length flags coasting, a spike in torsion flags a risky pivot, and a rising coherence penalty flags copy-paste answers. Because each component is interpretable, weights can be tuned to domain needs, more memory for tutoring, more controlled drift for planning, tighter torsion for safety reviews, while the underlying nDNA MTD signature preserves the full trajectory for auditing, clustering, and regression tests over time. More details on the equation and derivation in the book. We are looking at spectral memory retention, which is a score between 0 and 1 for each dial oak turn 1 to 30 and each layer 1 to 30. Think of 3 range bumpers as we talk. High, 0.70 and above, strong reactivation of prior context. Moderate, 0.40 to 0.70, partial recall, still workable. Low, 0.00 to 0.30, memory leak or noisy replay, with near zero meaning 0.10 or lower. Left, Llama. In early turns, 1 to about 13, across most layers, Llama holds high retention, typically 0.75 or higher, forming a broad, red plateau in the surface. After turn 13, retention declines smoothly from the high band into the moderate range as the dialogue shifts topics, which looks like controlled forgetting and intentional belief reorganization rather than collapse. If you stratify by depth, shallow layers 4 to 12, mid layers 13 to 22, and deep layers 23 to 30, you still see the same pattern, a long stable phase, then a gentle glide down, never an abrupt fall. That profile signals high spectral reuse of historical activations and healthy long-term coherence modulation. Right, Mistral. By contrast, Mistral starts lower and more irregular. Even in early to mid turns, 1 to 10, many layers sit in the low to lower moderate band, 0.20 to 0.45. Past turn 10, the surface drops toward near zero across a wide swath of layers, often 0.10 or below, indicating premature memory collapse and poor alignment between current beliefs and the learned memory subspace. Practically, this is where we expect forgotten constraints, stance reversals, and meandering answers. Bottom line. With these bumpers in mind, high greater than equal to 0.70, moderate 0.40 to 0.70, low or less than equal to 0.30, Llama exhibits a long high retention phase followed by gradual, structured decay. Mistral shows low, patchy retention that slides to near zero by the middle of the conversation. This contrast maps directly to episodic anchoring and multi-turn integrity. Llama carries context forward, while Mistral leaks it early. This slide shows thermodynamic length, which you can think of as the model's internal adaptation effort as it climbs layers within a turn. The surfaces sweep across layers from front to back and model slices left to right. The height and the color tell you how much epistemic work is happening. Cooler tones mean stable propagation with little change, while warmer tones mark substantial restructuring of the belief state. On the Llama panel, notice the punctuated, ridge-like bursts that are separated by calmer bands. That pattern is what we expect from modular, layer-specific realignment. The model concentrates effort right where a turn demands integration or a pivot, then quickly settles. On the Mistral panel, the effort looks broader and more diffuse. Instead of crisp peaks followed by consolidation, energy spreads across many layers and lingers. That suggests weaker modularity and more turbulent internal processing, where the network spends effort but doesn't reliably crystallize a new belief state. Takeaway: thermodynamic length exposes whether a model deliberates with intent, focused bursts that resolve or churns, diffuse effort without clean settling. Read alongside memory retention, drift, and torsion. It helps explain how the dialogue stayed on track or lost it. This figure is our epistemic drift vector field. It shows how the model's internal beliefs move from one dialogue turn to the next after we project them into a compact latent space. Think of each point as a layer-wise belief center at a given turn, and each arrow as the drift vector from that turn to the next. So direction tells you where beliefs are headed, and length tells you how much they change. Colors encode drift magnitude on a shared scale. Cooler shades mark small updates, essentially hold steady. Warmer shades mark large epistemic shifts, moments where the model substantially revises its stance or reframes context. The dashed gray curve is the baseline path. It connects the layer centers without directions, so you can see the overall route the model is taking through belief space, while the arrows show the local flow along that route. We've labeled layer indices to make the structure actionable. When you see a cluster of long, warm arrows around upper layers, that is late-stage reconfiguration, the network is injecting big changes near the top of the stack, often right before emission. That pattern correlates with last-minute rewrites, style overcorrection, or policy overrides. In contrast, short, cool arrows in lower and middle layers indicate stable representation building, evidence that the model is carrying forward earlier context and only adjusting gently as it reasons. Read this field in three ways. Flow coherence. Smoothly aligned arrows along the dashed path suggest guided progression. Jagged, crisscrossing arrows suggest semantic turbulence and a risk of losing the thread. Where the change happens. Concentrated drift in mid-layers is often healthy, integrating new facts. Concentrated drift in top layers can be volatile, surface-level edits without deep reconciliation. Asymmetry across turns. If the field shows strong forward drift followed by sudden reversals, you are seeing stance flips or goal resets. If drift steadily decays, the model is converging. How do we use this? First, as a diagnostic map, we can flag layers that repeatedly host large, misaligned shifts and target them for regularization or instruction tuning. Second, as an early warning signal, sequences of warm, misaligned arrows predict derailment before it appears in text. Third, for comparative evaluation, when you place two models side by side, the more reliable one tends to show shorter, well-aligned vectors with a smooth baseline path. The less reliable one shows noisy directions and late spikes near output. Takeaway: the drift field translates the abstract idea of the model changed its mind into a concrete, layer-resolved picture. It reveals where belief shifts originate, how they propagate, and when they become risky, turning epistemic drift into something we can see, measure, and fix. This slide is a curvature torsion view of belief flow over the dialogue. Think of curvature as how sharply the trajectory bends within its current plane. Small curvature means gentle steering. Large curvature means a hard turn. Torsion is the out-of-plane twist. It shows whether the model redirects its thinking into a new dimension rather than just turning on the same plane. Each plot traces one model across turns. The x-axis is the dialogue turn, the y-axis is curvature, and the z-axis is torsion. Line color maps curvature magnitude. Line thickness reflects torsion strength. Numbers mark the turns. A dot at the start and end helps you see the overall arc. On Llama, left, the trajectory shows moderate curvature with several torsion sign flips in the mid to late turns. That pattern looks like guided redirection. The model pivots the frame of reference a few times, but the bends are not extreme and the twists resolve rather than cascade. It suggests purposeful course changes that keep the thread. On Mistral, right, curvature is smoother on average, but we see episodic torsion bursts, short intervals where the line thickens and the torsion axis spikes. Those bursts indicate abrupt out-of-plane reorientations without much gradual bending, a signature of late, unstable pivots that can feel like topic jumps or stance flips. What to read from this view? High, persistent curvature means the model is constantly turning, risk of meandering. Sharp torsion spikes mean sudden reframing, risk of losing earlier commitments. Bounded curvature with brief, settling torsion, as in Llama here, signals healthier redirection. Paired with the drift field and thermodynamic length, this analysis tells us not just that the model changed course, but how it turned and whether that turn was stable or volatile. This slide looks at semantic coherence from two complementary angles so we don't confuse repetition with quality. On the left, we measure vertical coherence, how well each turn maintains a clean semantic abstraction across depth as activations move up the layers. Think of it as structural integrity inside a single turn. High values mean the representation tightens as it climbs. Low values mean the message gets muddier with depth. On the right, we measure temporal coherence, how stable the representation is across turns at the same layer. This is about memory alignment over time. High values mean the layer stays anchored to prior commitments. Low values mean the thread drifts. Together, these form an orthogonal pair. One catches intra-turn abstraction integrity. The other catches inter-turn memory alignment. Using only one can be misleading. For example, a model can look temporally coherent because it repeats itself while actually collapsing structurally within the turn, or it can keep a crisp structure per turn while forgetting what it said earlier. That's why we combine them with a simple weighted score, balancing structure and time. What do the plots suggest? Llama shows stronger vertical coherence early with a gentle decay and moderate temporal stability that holds the thread through the mid layers. Mistral shows shallower vertical profiles and faster temporal fade, a signature of answers that sound consistent locally but leak commitments as the dialogue progresses. Takeaway: coherence has to access. We want turns that sharpen with depth and conversations that hold shape across time. The unified metric lets us reward both and diagnose when a model is merely being consistent on the surface versus genuinely maintaining a stable line of thought. This table compares how well different automatic metrics agree with human ratings on multi-TurnDialogue. We look across 5 models and 5 dimensions: coherence, consistency, factuality, fluency, and engagement. The headline: Orbit tracks human judgment best overall, especially on the structure-dependent dimensions, coherence and consistency. Across models like Llama, Mistral, Gemma, Phi2, and GPT-Neox, Orbit sits at the top of the column for coherence and consistency and is competitive on factuality as well. That pattern matches Orbit's design. It reads the epistemic dynamics of a conversation, memory use, purposeful updates, and stable belief flow, rather than just the surface wording. By contrast, Blurt and GA will sometimes do a bit better on fluency and engagement, where stylistic polish matters, but they lag on coherence and consistency. Mauve, BERT score, and Persona show weaker alignment with humans on the harder multi-turn behaviors, often favoring surface similarity or single-turn signals. To practical implications. First, if your goal is dialogue reliability, keeping track of commitments, avoiding contradictions, and progressing sensibly, Orbit is the right primary metric. Second, if you care about style, like smooth phrasing or upbeat tone, you can complement Orbit with a fluency-oriented metric, but you shouldn't rely on those alone to judge multi-turn quality. Bottom line, humans reward conversations that remember, adapt, and stay on track. Orbit is tuned to those behaviors, which is why it aligns more closely with human judgment across models and tasks. So far, we've looked at local diagnostics, memory retention, thermodynamic length, drift, and torsion, measured turn by turn. Now we step back and ask for a global signature of the whole dialogue, a compact number that summarizes how the model's beliefs evolved across all layers and turns. That is what we call nDNA sub-MTD, a unified epistemic trajectory descriptor. Think of nDNA as an aggregate score built from 5 trajectory-sensitive signals, each with a clear interpretation and a tunable weight. First, the drift term. It measures the endpoint deviation in belief space, how far the conversation's final belief moved from where it began. Big drift can mean adaptation, but it can also mean derailment. We keep it, but we balance it with the other terms. Second, the Fisher-Grau term. This is the information geometric displacement along the path. It integrates the belief velocity, weighted by the Fisher information, so we count movement that is information-bearing rather than cosmetic. Third, the curvature energy. It penalizes instability in the update rule itself, the temporal variation of the Jacobian across turns. When this energy is high, the model keeps changing how it changes, which correlates with torsion bursts and brittle reasoning. Fourth, the spectral entropy term. It encodes memory retention. We estimate dispersion of representations in a compact spectral basis. Lower entropy means the model is anchoring to a stable subspace rather than spraying attention everywhere. Fifth, the belief action. Inspired by energy-based control, it couples the kinetic part, how fast the belief moves, with a potential that discourages unsafe or low-utility regions. This lets us nudge trajectories towards safer, more useful belief states. We average these components across layers and turns, with weights that reflect the task's priorities: more entropy control for tutoring, more curvature control for planning, more potential shaping for safety reviews. The outcome is a single, principled signature that complements Orbit. Orbit tells you where a dialogue went wrong, nDNA tells you how healthy the entire trajectory was. It is compact enough for dashboards and A/B tests, but expressive enough to explain robustness, stability, and learning over the course of a multi-turn conversation. Concluding takeaway with belief trajectories model by model. Stepping back across all views, memory retention, thermodynamic length, drift, curvature torsion, and the nDNA_MTD signature, the same pattern holds. Strong dialogue isn't about pretty sentences, it's about stable belief evolution. Systems that remember, spend effort where it matters, pivot cleanly, and follow smooth latent paths earn higher human trust. Orbit gives the turn-by-turn report card. nDNA_MTD gives the fleet-level health signature. Together they let us govern how models think, not just how they sound. Here's the quick, plain English fingerprint for each model. Gemma, composed and efficient. Trajectory, smooth, parabolic arc with minimal angular distortion. Signal, low curvature, high spectral coherence, clean energy bursts. Read, steady consolidation, updates land and then settle. Llama, purposeful pivots. Trajectory, moderate global drift with compact belief clusters. Signal, strong thermodynamic bursts at key junctions, torsion that turns on, does the job, and winds down. Read, flexible but anchored, adapts without losing the thread. Mistral, conservative but leaky over time. Trajectory, localized loops and short oscillations. Signal, lower entropy early, broader diffusion later, temporal coherence fades faster. Read, cautious updates that sometimes fail to carry commitments across turns. Phi2, curious wanderer. Trajectory, long, winding path with many small inflections. Signal, elevated torsion and Fisher-Rao energy, exploration outweighs consolidation. Read, rich probing but unstable settling, benefits from stronger memory anchors. GPT-Neox, turbulent and reactive. Trajectory, sharp angular jumps, occasional reversals, and broken segments. Signal, high curvature spikes, spectral entropy surges, late-stage torsion bursts. Read, prone to stance flips and policy-shaped rewrites near output.